Hello, everyone. My name is Wang Shuo, and along with my teammate Ziqian Luo, we are here to present our second place solution for the Kaggle competition on CryoET Object Identification. We will walk you through our methodology, key findings, and the results that led to our success in this challenge. Our presentation will cover the following key sections. We will begin with an overview of the background and motivation for the competition. Then, we will summarize our approach, followed by a discussion of feature selection and engineering, the training methods we used, and the important findings we encountered during the process. Finally, we will highlight the performance of our simple model and conclude with a code review. We will also leave time for a Q&A at the end. Here is the background of our team members. Ziqian Luo is a sophomore student majoring in artificial intelligence at the University of Science and Technology of China. He has previous experience as an intern at Xiaomi, where he worked in the automotive department, focusing on simulation algorithms for autonomous driving. Ziqian's motivation for participating in this competition was to gain hands-on experience in model training and acceleration. As for myself, I'm a computer vision and deep learning algorithm engineer at AI Pro, where I develop algorithms focused on workspace safety solutions. My professional background includes work in medical image segmentation and object detection. I regularly participate in Kaggle challenges to further my research and technical expertise, and the G competition was perfectly aligned with my interests in segmentation and object detection. Let's now look at the summary of our approach. In this competition, the objective was to detect CryoET objects from 3 tomograms. During the training stage, we generated training labels using a customized mask radius, split the tomograms into subtomograms, and trained multiple lightweight segmentation models with parameter sizes ranging from 873,000 to 14,200,000. Moving on to the inference stage, we divided the test tomograms into subtomograms with size of 128 times 384 times 384, and the overlapping regions of 32 times 32 times 32. Each subtomogram was then processed by the model. After inference, we mapped the predicted subtomograms back to the original tomogram and reconstructed it. We used the CZII algorithm to convert the segmentation results into particle clusters, followed by post-processing strategies, such as threshold-based clustering, size filtering, and coordinate conversion. Feature selection played a crucial role in our approach. We selected the appropriate segmentation masks based on the particle types and their corresponding radio state. The competition dataset only provided coordinates, so generating the correct radius for each particle type was vital. For instance, the apoferritin particle had a default radius of 60, which we adjusted based on our approach. Regarding the subtomogram sizes, we experimented with multiple patch sizes. Each size influenced the model's performance. For model architecture, we used various networks such as UNet, VoxResNet, DensethNet, VoxRNet, and UNet with 2D encoder, 3D decoder. We compared the performance of different models to identify the optimal architecture for the task. To address the imbalance in our dataset, we utilized a data sampler that ensured balanced sampling during training. Additionally, we applied extensive data augmentation techniques, given the limited number of training samples. This helped in improving the model's robustness and generalizability. To further tackle class imbalance, we employed Tversky loss, which allowed us to control false positives and false negatives by adjusting the alpha and beta values. We also incorporated cross-entropy loss to penalize incorrect predictions, further optimizing our model's performance. In terms of training hyperparameters, we used the AtomW optimizer with a learning rate of 0.001 without a learning rate scheduler. Our training was conducted for 100 to 200 epochs, depending on the model. We used batch sizes, ranging from 2 to 8 subtomograms, and our hardware setup included a GeForce RTX 3090 with 24 gigabytes of memory. During training, we noticed instability in the model's performance, particularly when using batch norm 3D and ReLU layers. This led to fluctuations and challenges in convergence. By replacing these layers with instance norm 3D and p-ReLU layers, we significantly improved training stability and achieved more consistent model performance. Another interesting challenge we encountered was the presence of border artifacts during the reconstruction of subtomograms into full tomograms. We tested various kernel types, including uniform, Gaussian, and customized kernels, to mitigate this issue. Our experiments showed that the customized kernel resulted in the best performance, effectively reducing the artifacts. Our best performing single model achieved a private pound score of 0.767, which represents 97.7% of the highest score obtained from our 10 ensemble model. This success can be attributed to several factors. The use of instantanorm 3D combined with p-relu activations, a downsampling factor of 1/4, and the implementation of residual blocks to prevent overfitting and improve parameter efficiency. For those interested in the technical details, you can access our code repository on GitHub, which contains all the scripts and configurations used in this competition. This provides insight into our approach and the methods we employed to achieve our results. In summary, this competition allowed us to explore advanced techniques in 3D object identification and segmentation. Through strategic model selection and rigorous experimentation, we achieved strong performance. We appreciate the organizers for this valuable challenge and thank you all for your time. We are happy to take any questions.